So, welcome back to the wonderful world of carbohydrates. And we've kind of taken a back burner now on the reactions. The good news for you is that all the videos that you've watched so far, this concludes the reaction portion of the carbohydrate lecture. See, that wasn't so bad, was it? We started off with a little bit of what happens to a carbohydrate when you put it into a base, and then we went through the oxidation and reduction, then we went through Kalani-Fisher and the Wohl degradation. So other than maybe one or two that are out there remaining, this is basically it. But before we go further and before we talk about these extra reactions that carbohydrates can undergo, I want to return back to structure for a moment, because we don't need to take something for granted. And that's this structure, that this Fisher projection that we've drawn over and over and over and over, right? So I'm going to draw the structure for glucose here, and I'm going to draw it as far as the Fisher projection is concerned. So glucose, we know, is a 6-carbon chain, and the OH groups go right-handed and left-handed and right-handed and right-handed. So we know that this is the location of the OH groups themselves, the hydroxyl groups. And we've called this glucose, and we've called this D-glucose again because the last OH group is over to the right. So because of that, that is dextro, which is right-handed. Okay, so this is what we've been looking at as far as structures are concerned. Notice this is the structure that we started off with. These are the structures that are in your table. These are the structures that we have looked at as far as the reactions go. This is your typical carbohydrate structure. We call this the open chain structure. Open chain. And the reason that we call it the open chain is because this is not the only structure that's out there. I mean, as far as the reactions go, as far as identifying and labeling and drawing just the bare bones carbohydrates, then that structure will do us just fine. The problem that we have to understand and that we have to deal with is that these carbohydrates make circles around us. Okay, so what does that mean? Well, that means that the carbohydrate, depending on the length of the carbohydrate, well, it can take this kind of chain with this backbone of a head and a tail, and the head can actually turn around and bite the tail of the chain. And all of a sudden, what we end up with is basically a circular molecule, a ring. So all of these carbohydrates, every one that we've mentioned, for the most part, at least if they've got 4 or 5 carbons in them, can turn around and they can make a ring on themselves. Okay, so when we talk about ring structures, we have a proper term that we use for that. And that proper term that we will begin using to describe how we draw these rings of sugars is a Haworth projection. Haworth. A Haworth projection. So we've got a Fisher projection that shows the straight chain sugar with a head and a tail and the H and OH on the backbone. And then we have Haworth projections that basically represent these ring formations that the sugars begin to undertake. So we're going to have to get comfortable, just like we did with cyclohexane back in the day, of drawing structures that are rings that represent carbohydrates. It's very, very important. It's almost as important as the reactions are out there, right? Okay, so first off, we've got to talk about why and how these rings basically happen. That's one of the first things that we have to figure out. You know, what is really causing this intramolecular reaction? Because that is what's happening here. Intramolecular, meaning within the molecule itself. There is a reaction within the molecule itself that's making it basically come around and biting its own tail. Okay, well, here's the issue. If you go back to the carbonyls, and this is where the problem lies. We're looking at the carbonyl reactions. We know that a carbonyl will react with a OH group. We saw that in the carbonyl lectures. If you forgot those reactions, go back and take a look at them. However, the only one that we're going to be looking at is mechanism here, because this is one of those instances where I think mechanism is a fair game, right? I mean, this is bare bones, minimal organic as far as carbonyl goes. So if I look at my carbonyl group, it's right up here at the top. So here's my carbonyl group, right? And this oxygen's electronegative. This carbon, it's getting electrons pulled away from it. And just like we saw back in the day, this carbon's partial positive and this carbon is partial negative, just because of that electronegativity difference. That carbon's electron greedy, it's an electron puller, it becomes negative, and that poor carbon involved in the double bond, it's getting everything pulled away from it, so he becomes positive for that reason. So we begin to see basically a reaction that happens here between a positively charged carbon. Now, what's going to be looking for a positively charged carbon? Well, what we would prefer to happen, or what would the reaction prefer to happen, is that we would need to find something negative. And this is going to look out and react with anything that is slightly positive. Now, we know that this oxygen up here at the top, that is slightly negative. But you know, this oxygen has a negative charge, and this oxygen's got some free pairs, so that's a negative charge. This oxygen has some free pairs, that has a negative charge. And this oxygen has some pairs, that's a negative charge. And this oxygen's got some pairs, that's a negative charge as well. So we've got negative charges scattered throughout the entire molecule. So that means we're going to have to figure out maybe which carbon would be best suited, or which hydroxide at least would be best suited to react with the carbon of the carbonyl group, right? Okay, well, I can go ahead and tell you it's not going to be number one, because if we try to make a chain here, or a ring between the carbon and that oxygen, we are going to get a two-membered ring, and that's not going to work out for us, right? We've talked about ring stability back in the first organic class that you took, and we said that 2 carbon rings are not very good. 3 carbon rings, they're a little bit better, but they're still not good. 4 carbon rings are a little bit better, but they're still not stable. 5 carbon rings, well, we kind of get some stability there. So if we can get a 5-membered ring in some form, the carbohydrate could possibly become happy. And then a 6-carbon ring, or a 6-membered ring, that's really what we need to focus on here. A 6-membered ring is even more stable than a 5-membered ring. So if we can get a 6-membered ring out of this thing, then the carbohydrate can make a ring structure, and that ring structure is going to have some stability. Okay, so here's carbon number 1. And here's carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. So I'm going to number these. 1, 2, 3, 4, 5, and 6. Now, pay careful attention to the words I'm getting ready to use. I did not say a 6-carbon ring is what you're after. I said that a 6-membered ring is what you're after. The 6-membered ring is more stable than any of the other rings. Now, it can be carbon that's there, or it can be a mixture of carbon and other elements. And these other atoms make it a heterogeneous ring and not a homogeneous ring, right? We get carbon and we get other things involved at the same time. So the problem that I have here is that many people will try to take carbon number 1 and carbon number 6 and try to hook them up together to make the ring. And that is a no-no. That is not what you want to do here, because that's not really what's actually happening, right? This carbon is not the one that's attacking that carbon. Carbons are not going to be attacking the other carbons in this molecule. It's the negative oxygens in the hydroxyl groups that are attacking the carbon. So here's where the problem lies. If I take carbon number 6, and I understand it's not carbon 6 that's going to do the attacking, it's actually the oxygen that's doing the attacking. Okay, well, how far down is that oxygen located from this carbon? Well, this is spot 1, spot 2, spot 3, spot 4, spot 5, and that's spot 6. The problem, though, is that you have to count that carbon as a spot as well. So there's 7 spots. That means that this ring that I will form if I target this OH group is going to be a 7-membered ring. And this is a no-no. This ring is too floppy. We don't want floppy rings. We want stable rings. The sugars want to be stable if this is what's going to happen to them. So that last OH group is a no-no. And the last carbon is a no-no as well, because it's not the carbon that's doing the hookup. It's the oxygen that's doing the hookup. So where is kind of the prime spot for this circular reaction to take place, this intramolecular reaction? Well, the prime spot, if this is the first atom in the ring, this is the second atom, that's the third atom, that's the fourth atom, this is the fifth atom, that means this OH group would serve as the sixth atom in the ring. So this OH group is going to be attracted to that carbon. And if they can do the hookup, and if they can hook up at that spot, then what you will see form is a 6-membered ring. Okay, so how do we draw that before we run out of time? At least let's draw this ring structure that we've spent 12 minutes talking about, right? Okay, so we start off with the carbon in the carbonyl. So I'm just going to draw C double bond OH here. That carbon is attracted to another carbon that has an H and an OH. I'm going to leave those off for a minute. That carbon's attracted to another. This is the third carbon in the chain that has an H and an OH on it. That carbon's attracted to another one. That's the fourth carbon in the chain, right? This carbon's attracted to another one. That's the fifth carbon in the chain. And we said that that fifth carbon has the OH group on it that will do the connecting to make this 6-membered ring. Off of this fifth carbon, we have a sixth carbon, so I can kind of draw it up like this, and that also has an OH group that's hanging off. Okay, so this is carbon number 1, and this is carbon number 5. And we see a reaction that happens here. If I want to show curvy arrows, I can. Curvy arrows here are fairly easy. We get some dots that are here. These electrons are attracted to the positively charged carbon. That carbon basically breaks the bond to that oxygen. It gives the oxygen the electrons. We form a new bond here between this oxygen and this carbon, and we get some rearrangement that happens. So down here below, I'm just going to skip some of that mechanism and some of that rearrangement because it's not that important, at least not yet. And we see this ring form where here's the oxygen of the OH group, and it comes around and it connects to the head carbon. Okay, so that's the formation of a 6-membered ring. So 6 carbons, hexoses. That's the take-home message. Hexoses form 6-membered rings, right? And the ring consists of 5 carbons and 1 oxygen, right? Now, if we have a pentose, a 5-carbon ring, well, they form ring structures as well, and we'll see that in the upcoming video or two. But for now, I want to focus on the 6-membered ring. There's more things that we need to talk about this ring, and there's more kind of dig a little deeper moments that we need to have before we go further and talk about modifications of this intramolecular reaction. So, what we're seeing happen is that these straight chain sugars can actually turn around and react on themselves at the 5th position, the 5th carbon, to form these ring structures.